Another application of this rate of change mindset, equating a original function with its derivative, is this. Something called Newton's law of cooling. You guys are all familiar with Sir Isaac Newton, one of our founders of calculus. Also has 3 wonderful physics laws that we all beat to death every year when we take a physics class or whatever. Newton also came up with this idea behind, basically, the idea of an object cooling. And he noticed that when he was analyzing objects in their cooling states or whatever, that the rate of change of a temperature of an object is proportional to the difference between the temperature of that object and the surrounding temperature. Now that's a quote from Sir Isaac Newton. Let's convert it to calculus. Sir Isaac Newton noted that, quote, the rate of change of the temperature of an object. What does rate of change mean to you? Derivative. So the derivative of the temperature of an object, that would be big T there, over little t with respect to time. So big T is temperature, little t is time. So the derivative of temperature with respect to time is proportional to, is equal to some constant proportionality k times the difference between the temperature of the object and the surrounding temperature. The difference means I'm going to subtract the temperature of the object, which we call big T, minus T sub s, and T sub s is the surrounding temperatures. Okay? Does that make sense? Now, when we get you guys into DFQ, we're going to explain how to actually do antiderivatives and actually solve for big T. We're just going to give you the equation here. Yes?
Is that big T for time supposed to be a lowercase t?
This one right here is a lowercase t.
No.
That's a big T for temperature.
In the box on the bottom left where it says t equals time.
Oh yeah, typically that's going to be a lowercase t there. You understand, when we type these things in, what we got is T. So, but T is time, big T is temperature, little t is time. Okay? So, the solution for this thing is this. Because the rate of change of the temperature is proportional to itself minus some constant, you're still going to have it looking like this. The temperature of an object with respect to time is equal to CE to the KT plus TS. This is your modeling equation solution. Okay? Where C is some kind of a constant, we're going to have to solve for that. It's not just the initial constant, it's a little more than that. And K is your growth or decay rate of the temperature. Now, honestly, we use this type of equation when we're doing forensics. You know, finding dead bodies and having to figure out who done it on television and actually real life, called the coroner. Okay? That what the coroner does is this. All right, so you come across a crime scene. Police officer runs across a crime scene. You got a dead body sitting there. Okay? What's the first thing police officers are supposed to do? First thing. Rule of thumb, police officers. What they got to do? Cordon off the area and call in backup and call the coroner. They got to basically, for evidence purposes, they want to kind of surround off the area, make sure people aren't trudging through this thing. One. The second thing they got to do is they got to get the coroner there. So they immediately call the coroner. The coroner shows up there. They're looking for all kinds of evidence, you know, guns, bullet wounds, knife wounds, whatever, the big club, the frying pan that hit the guy in the head. Okay, something like this. We got to figure out what exactly happened here. Police officers are looking for evidence, right? The coroner comes there to inspect the body, to look at evidence on the body. And the first thing I'm going to try to do is try to figure out the, quote, time of death. Now, here is your modeling equation for the dead body. It's the Newton's law of cooling formula. But if you look at this thing, you'll see that, one, you got TS. What does TS stand for? What does TS stand for down here? Temperature of the surrounding area. So they're going to take a temperature surrounding, whether it's in a room someplace, in Fretwell or Denny Building, okay, they're going to figure out what the temperature of the room is, or if that's outside, they're going to take the temperature of the outside, okay, and try to figure out what the temperature is. Second thing they do is once they get the surrounding temperature, you'll notice in this formula you have two constants, C and K. So they have to take an initial temperature for every constant that they have to solve for. We have a C and we have a K. So there's two things they have to do. I have to solve for to get the modeling equation, which means the coroner traditionally takes just two temperature readings of the body. So when the coroner first gets there, he notices his clock. He pushes a button on his clock. It's right now at 2:20 in the afternoon, and he takes the temperature of the body. Well, let's get gory about this and talk about real forensics here. How does the coroner take a temperature of the body? What's that? Well, yes. What, does he stick it under his tongue? He may not have a head. I don't know. So, got to be cool about this. So, it's a real crime scene here. Where they stick the thermometer in is actually the liver. They'll make an incision and stick the thermometer in the liver. Why the liver versus any other organ that happens to be there? Yeah. Its most central part. It's surrounded by all other kinds of material and body parts and stuff, so it'll be the most consistent on temperature. That's why. So they'll stick a thermometer in the liver, not under the tongue, okay, or the armpit, because you may not have one of those either. So you stick it into the liver, and they takes the temperature of the body. And then he waits a little bit of time, 30 minutes, an hour, depending on how messy the crime scene is, what other type of jobs they have to do, and then they'll take another temperature. They take two temperatures of the body. That's all they need, because with the surrounding temperature and the two temperatures of the body, they can actually get the mathematical formula that will actually get the dead body. Now, why do they need that? Because what they're going to do with this mathematical formula is this. They are going to set the original body temperature at what? 98.6. That's when the guy was alive, and then work their way backwards to try to figure out at what time did the crime get committed. Does that make sense? And so with their 2:20 and they work their time backwards, they can mathematically calculate approximately what time the crime was committed. So that's more information for the police officers, and then they can go for their suspects and go, okay, where were you at 1 o'clock this afternoon? And then basically look for the people that don't have alibis and actually were in the area, that type of thing. So it's very CSI forensic type stuff here. But this has actually been a formula around here since about 400 years. Okay? So it's called Newton's Law of Cooling. But, you know, I'll give you guys a nice, cool dead body problem later. But for this particular problem right here, we have, well, it's getting close to Thanksgiving. Let's go a roast turkey here. We have a roast turkey taken from an oven when its temperature has reached 175 degrees Fahrenheit and is placed on a table in a room where the temperature is 65 degrees Fahrenheit. If the temperature of the turkey is 55 degrees Fahrenheit after a half an hour, what is the temperature after 45 minutes? So I've got all this information right here, and basically you got to tell me, okay, they pull the turkey right out of the oven at 175 degrees. Basically, 45 minutes later, what's the temperature of the turkey? That's what we want to know. Is it ready to eat, or is it still too hot, that type of thing? Is it still warm? You know, is it too cold when you stick it in a microwave or something like that? That's what we want to know. Let's do it mathematically here. All right. So roast turkey is taken from an oven when its temperature has reached 175 degrees. Okay? So right there, that 175 degrees is the initial temperature of the turkey. We just took it out of the oven. 175 degrees Fahrenheit. And it's placed in a room, on a table, in a room where the temperature is 65 degrees Fahrenheit. So what is that 65 degrees Fahrenheit? That is the surrounding temperature. Okay? So we got some information here. T surrounding, 65 degrees Fahrenheit. The initial temperature of the bird is 175 degrees Fahrenheit. And we know another piece of information. If the temperature of the turkey is 155 degrees Fahrenheit, 155 degrees Fahrenheit, after a half an hour. Okay? Temperature after half hour. Here's the question. Always quote your question before you do the problem. What am I looking for? The question is, what's the temperature of the bird? Okay, what's this temperature after 45 minutes? When time equals 45 minutes. And this is what I want you guys to focus on. You got problems with this one. You got unit problems. Always pay attention to units. They're sitting there talking about, you know, initial temperature, and then they talk about half an hour later, it's 155 degrees. Now they want to talk about 45 minutes. You got to be consistent. When you're consistent, focus on a particular time. It doesn't matter which time you focus on, but make sure you use only those units. So they're talking about hours and minutes. Which one do you want to stick with? You want to do the problem in hours? You want to do the problem in minutes? You want to do it in minutes? Fine. Your choice. Just pay attention to web work and what they're asking for when you do this. All right, you decided minutes. So a half an hour would be what officially then? We're going to be consisting to minutes, so that would be the half an hour is 30 minutes. Okay? So, here's my equation. That is the Newton's law of cooling formula. Big T of C equals C, big T of little t equals C e to the k times little t plus Ts. Big T of little t equals C e to the kt plus, what's the surrounding temperature? 65. Always start with the initial temperature, because I have two particular temperatures, because I have two particular constants I need to solve for. Always start with the initial. Temperature at time equals 0 is 175. So temperature at time equals 0, 0 minutes is 175 equals C e to the kt plus, key where t is 0, times 65. Clean it up. 175 equals C. What's k times 0? 0. What's e to the 0? 1. So k times 0 is 0. E to 0 is 1. That goes away. Plus 65. Subtract 65 from both sides. I believe that's 110. I figured out what the C has to be. C is equal to 110. I plugged in time as 0, and then I had to solve for big C. That gives me the equation big T equals C, which is now 110, e to the kt plus 65. But there's still another constant I need to know. That's where we're going to use the next condition, initial condition, which was what? After 30 minutes, the bird reached 155 degrees. So temperature is now 155 equals 110 e to the k times 30 plus 65. The only thing solved for is k. It's the only variable left. What's my first move? If I'm trying to solve this equation, and I'll blow it up for you guys in the back there. If I'm trying to solve this equation, 155 equals 110 e to the k times 30 plus 65. What's your first move to solve for k? Subtract 65. Get the term with the e in it by itself. So I'm going to subtract 65 from both sides. And 155 minus 65, that's pretty easy. That's just 90. So that's going to give me 90 is equal to 110 e to the 30k. Just cleaning it up a little bit. What's your next move? Now you got the term with the k in it by itself. Now I want to get rid of the coefficient to get the e part by himself. So what's my next move? Divide by 110. And 90 divided by 110 is actually, what is that, 9/11? Yeah. 9/11, might as well reduce fractions. 11ths there, John. Good. 9/11 equals e to the 30k. And now what's your next move to get that k by himself? Natural log both sides. Natural log, so that natural log cancels, leaving me with the natural log of 9/11 is equal to 30k. Divide both sides by 30 and end up getting k. K is equal to natural log of 9/11 divided by 30. And I got a negative .0066 .6689022. Double check me on that, but according to my math, that's what I got. Question? Yes, you would have gotten a different K, but the answer to the question will still be the same. I still haven't answered the question. All I'm doing is figure out the puzzle. So if you wanted to convert this thing into hours, you're going to get a different K value. Your formula is going to look slightly different with a different K value up there. But once you answer the question, watch, we'll both get the same answer. Except mine will be in minutes, yours would have been an hour. So yours would answer would have been like 1 hour. I would have gotten 60 minutes is the answer. But when we convert, we get the same thing. So there's my K. Therefore, my modeling equation is big T of little t equals C, which was 110, e to the K, which we now know to be negative .00668902232 times T. There it is. There's my modeling equation. Oh yeah, what was the question here? What do we want to know? Question. What's the temperature of the bird after 45 minutes? We converted all my time units to minutes, so that K is a minute K value. Does that make sense? So, well, to answer my question, because that's the most important, is getting the modeling equation, because once you get that, you can answer any question. But now we want to know what the temperature of the bird when time equals 45, right? So this is 110 e to the negative .0066890232 times 45. Just plugging in time is 45. Double check me on this, but I got 110, just type in on my calculator, e raised to the negative .066890232 times 45. Plus 65. I knew there was something was wrong. Plus 65. Thank you, darling. Lost my plus 65. There's my modeling equation. Just don't forget to add that plus t. Plus 65. Plus 65. And what do I get? I got 146.408063 watt. Degrees Fahrenheit. Does that make sense? Now, of course, this is the internal temperature of the bird. I think I'm all right if I'll slice off a couple of slices on the outside and go ahead and start munching on it. But the internal temperature of the bird is still going to be quite warm. Does that make sense? Did I lose you guys anywhere on that? Yeah.
When you got at this second line from the bottom, we've got T temperature of time equals 45, 48.
That's 45 right there. Yeah. T of 45. That was our question. Remember back over here we wrote it down? What's the question was in this particular problem, part A, what is the temperature after 45 minutes? So I'm looking for time equals 45. So I'm taking my equation, plugging in 45. That's, believe it or not, that's my 45. And it's 110 e to the .0066689. Notice I use all the decimals, so I'm thinking web work. Plugging in 45 for T and adding 65 to it. Does that make sense? And if you had converted this problem in terms of hours and used, let's see here, half an hour would have been 1/2. 45 minutes would have been what, 3/4? You would have typed in time as 3/4, but at the end of the day, we would have gotten the exact same temperature. Good. Does that make sense? All right, let's keep going. When, a question of time, will the turkey have cooled down to 110 degrees Fahrenheit? Well, there's my modeling equation, because that's the most important thing is get your modeling equation. Big T for temperature equals 110 e to the K, which was negative .00668902232T plus 65. There's my modeling equation. What are we going to do to this problem? Cool down to 110 degrees Fahrenheit. So temperature is 110. That'll equal to 110 e to negative .00668902232T plus 65. Basically, I'm solving for time on this one. When's a question of time. But watch, this is this is what's going to happen to you guys on web work. You can do this. You decided to do all this stuff in minutes. That time right there, because that K value represents in minutes, that time is going to be in minutes. So when I solve this thing, it'll be in minutes. So I'm going to subtract 65 from both sides, get my term by himself. 110 minus 65 is a whopping 45. 45 equals 110 e to the negative 0.00668902332t. What's my next move? Divide by 110 on both sides, get that e by himself. What's my next move? Take the natural log of both sides. Actually trying to kill off some steps here, so the natural log and e cancels. And what's my last move to solve for t? I'm going to divide by the negative 0.00668902332. And again, I use all the decimals because I'm assuming this is a web work problem. 668902332. So this cancels, and that gives me t is equal to, and I'm just going to type this in on my calculator here, the natural log of 45 divided by 110 divided by that k number. And it's negative, don't forget the negative, 0.00668902332. And I end up getting 133.62457444. What? Minutes. That is my answer. But watch web work. Web work is going to ask you same question, but then they have to be specific. They wanted time to be in hours. Well, I'm sorry, I didn't do hours. That's all right. You can convert your answer to hours to make them happy. Because if you type this in on web work, and it's, even though the answer is minutes, and it's the correct answer, you want it in hours, they're going to say, wrong. So how do I convert it? Right. So I take my answer. Remember, there are 60 minutes in an hour, so I'll divide this by 60. Divide by 60, John, that helps. Divide by 60, and what do I get? I got for hours, t equals 2.22707624 hours. Does that make sense? And let's say I wanted to be mean and I put it on the test. I want the answer in hours, minutes, and seconds. Okay, good. Great engineering problem. We need the answer in hours, minutes, and seconds. How many hours is this? 2 hours. So I got my answer. There it is. And you see me divide by 60 there. I'm going to subtract off the 2 because the decimal part of this answer, that 0.227076244, is actually a fraction of an hour. It's a decimal of an hour. But how do I convert that 0.22707 hours into minutes? Oh, what do you do? It's now in hours. I want it back into minutes, so I'm going to multiply by 60, and that gives me 13 minutes. But keep on going, but you see that 0.624574442, the decimal part? That's a decimal of a minute. A fraction of a minute, we like to convert it to seconds. So I'm going to subtract off 13 so I can just focus on the decimal part. And this is in minutes, 0.6 of a minute here. I'm going to multiply that by 60 because there's 60 seconds in a minute. And that tells me it is, I guess I can round it off to the nearest second here, 37.5. You guys good on that? 37.5 seconds. So, after 2 hours, 13 minutes, and 37.5 seconds, the bird has reached 110 degrees Fahrenheit. Does that make sense? Did I lose you guys anywhere? Again, wanting you guys to get used to this conversion factor in numbers, pay attention to units, especially on test, homework, and web work, and therefore you'll be paying attention to it on final exams. See you guys later.